In this video, I want to introduce general polar regions and show you how to compute double integrals over such regions. Suppose we have a polar rectangle R, whose polar coordinates are both bounded by constants. How can we extend this to a more general region? Well, first, we can replace the lower and upper bound for theta by two functions of R, while the variable R is still bounded by two constants. Or we could replace the lower and upper bound for R by two functions of theta, while the variable theta is still bounded by two constants alpha and beta. Okay? Let us now visualize the general polar regions. So suppose we have a region D where the polar coordinate R is bounded by two constants. This means the region is bounded by two circles. You see, the smaller circle is a circle of radius A, which looks something like this, and the larger circle is a circle of radius B, and our region D lies between these two circles. Furthermore, for every such R that we choose, the angle theta will be bounded above and below by some functions of R. And to visualize this, we can fix a particular R. So let's say we have one R between A and B. So let's say we have a circle between these two circles. Let's suppose the radius of this circle is R0. So this is a number between A and B. Okay? So the equation of the circle is R equals R0. Now, what happened to the angle theta? Well, the bounds on theta say that the region must be bounded between two rays. The first one is given by the ray theta equals G1 of R0. You see? Let's say G1 of R0 is somewhere here. So that would be one of the ray, which is the lower bound for theta. The inequalities tells us to increase the angle until we reaches the upper bound. In other words, we must be drawing all these rays cutting through the region until we reach the upper bound. So let's say the last ray over here is this one. Then the equation of this ray will be theta being equal to G2 of R0. So basically, we're including all the intersection points of these green rays and the blue circles. Do you see that? So for every fixed radius R0, the region D consists of all the points following the arrows starting from the first ray here, following the circle until it reaches the upper bound. So this purple arrow represents the points on the blue circle that must be included inside our region D. Do you follow me? Now we can repeat the same procedures for different radius of our circles. Then we're going to get a bunch of arrows with possibly different starting and ending points. And they're all parts of a circle between A and B. In other words, we're going to get arrows that look something like this, covering the entire region D. And notice the starting points of these arrows may not be the same, and also the ending points may not be the same. And if we join all the starting points of these arrows, that will form a curve whose equation is given by theta being equals to G1 of R. And likewise, if you join all the ending points of these arrows, we'll get a curve theta being equal to G2 of R. Alright? Let us now look at the double integral over such region. So suppose we have such a polar region D then the double integral over this region D can be computed by turning it into the following iterated integrals with respect to r and theta. And over here, we're going to place the variable r at the most outer integral, because this is the only variable which is bounded by constants. Okay? So here, the variable r must be placed outside, and the corresponding limits of integrations are a and b respectively. For the inner integral, this will be an integral with respect to theta, from the lower bound g1 of r to the upper bound g2 of r. As before, we're going to replace dA by r d theta dr. So again, do not forget the additional r in the conversion. And also, the function f of xy will be replaced by a function in terms of the polar coordinates, where we have replaced x by its corresponding expression, r cosine theta, and y by r sine theta. Alright, so this is the formula for computing a double integral over such a general polar region. So the thing to note here is that we are not allowed to simply swap the order of integrations. The order has to be d theta dr, where the variable r is placed at the most outer integral. Right, let us move on to the second type of general polar region. Well, this time, the angle theta will be bounded by two constants, whereas the variable r will be bounded by two functions of theta. Well, the fact that theta is bounded by two constants means that the region D lies between two rays. See, the first one here will be the ray theta equals to alpha, and the second one is the ray theta equals to beta, and the region D is between these two rays. Right, so let us now look at what happened to the variable r for a fixed ray between alpha and beta. So suppose we have a fixed angle, let's say theta naught. Let's look at the equation theta equals to theta naught. In other words, let's look at a ray between the lower and upper bound for theta. The variable r will start from h1 of theta naught. So we're going to have a circle of radius h1 of theta naught. And let's suppose h1 of theta naught is somewhere here. Then we're going to have this circle whose radius is equal to this number. Okay? And likewise, the upper bound is another circle, r equals h2 of theta naught. So let's say h2 of theta naught is somewhere here. Then we have another circle which looks something like this. The bounds on r tells us to include all the circles between these two circles. So we're going to look at all these circles between these two circles intersecting the region D. Okay? And now all the intersection points between the ray in the middle here and the blue circles are those points on the ray that must be included inside our region D. Do you follow me? In other words, the arrow starting from this point, following the ray until it reaches the upper bound, the entire arrow will be included inside our region D. And we can do this for other rays as well. So if we change the fixed angle, then we're going to get a bunch of arrows, okay, following rays, covering the entire region D. But notice the starting points and ending points of these rays may not be the same, because in general h1 and h2 are functions and not constants. So if we join all the starting points of these arrows, we'll get a curve whose equation is given by r being equals to h1 of theta. And likewise, if we were to join all the ending points of these arrows, we are going to get a curve whose equation is r being equal to h2 of theta. Are you with me? So all these green arrows will give us the region D for this particular polar region. Let us now look at the double integral formula over such region. Well, again, we can compute this double integral by converting it into an iterated integral with respect to r and theta. And this time, the variable theta will be placed in the most outer integral, because this is the only variable which is bounded by constants. Again, the term dA will be replaced by r dr d theta. So do not forget the additional r in the conversion. The inner integral is an integral with respect to r from the lower bound h1 of theta to the upper bound h2 of theta. And as before, both x and y will be replaced by their corresponding expressions in the polar coordinates. The thing to note here is that we are not free to change the order of integration anyhow we like. The variable in the outer integral must always be bounded by constants. In this case, theta will be placed at the most outer integral. Okay guys, in the next video we'll see some examples using these formulas. Stay tuned.